Hello, everyone. We are going to wrap up chapter 12 today with some graphing. It's going to be slightly more complicated graphing than we've seen before, but it's still pretty basic, and there's not a lot of material in this section, really just kind of like one trick, and that's going to allow us to graph just a bunch of stuff in R3. Okay. So we're going to be graphing slightly more complicated things, as I said, and this technique we're going to use, we've kind of used it already before, at least I have, as I was drawing stuff during these lectures. It involves this idea of something called a trace. Okay, so what is a trace? The technical definition is, okay, it's the intersection of a surface and a plane parallel to one of the coordinate planes. Okay, so what does that mean? Think of it as you have this 3D object or 3D surface. I'll say a surface in R3. How about that? It's a better way to phrase it. So we have a surface in R3, and then we're going to take a slice out of it. So think about it like you're cutting a slice out of the surface that you might put on like the slide of a microscope. Okay, so like a very thin slice. Okay, and if we take a bunch of those slices and kind of stack them up, we kind of see what the 3D object looks like, right? So maybe drawing the 3D object, just looking at an equation and drawing this surface in R3, maybe that's really difficult. But if we just kind of think about taking these slices and then draw these curves in R2 and then stack them up on top of each other, maybe that's a bit easier way to get an idea of what's going on. Okay, so really easy example, and one I think we've seen before in previous videos. Let's try and graph this thing in R3. So x squared plus y squared equals 4. First, let's start by thinking about slices again. Okay, so let's say I take the slice through the plane z equals 0, right? Remember what z equals 0 means. This is a plane. What plane is it? It's the plane where z equals 0, so z equals 0 right there. And basically we're talking about this horizontal plane, the plane of the xy plane, right? Okay, so we're confining ourselves to that. And when we confine ourselves to that, okay, forget about the other dimensions. Just think about that horizontal plane, okay? If I was working in a horizontal plane, what would that equation be? X squared plus y squared equals 4. Well, that would be a circle with radius 2, right? Okay, so if I just think about that plane, okay, maybe let's do it in a different color. Yeah, maybe we'd get something like, I'll try and draw this nice. Yeah, it's pretty good. Okay, so I'll get this circle in this two-dimensional plane, this xy plane. Okay, so that's what it looks like when we take this slice through the plane z equals 0. If you want to think about it, okay, maybe we have this plane, right, through z equals 0. We take that slice, and then inside that slice is this curve. Okay. Now we don't care about the plane. We just care about what's inside the plane, that shape. Okay, so we got that thing inside the plane. Now let's take a couple more slices. Okay. Got okay. So we maybe I move up to z equals 2. Okay. So now let's look at this plane. Well, let's go a bit. Yeah, z equals 2 is fine. So now let's look at this slice through z equals 2. Okay. Again, I have this plane through z equals 2, right? This horizontal plane, but it's moved up a couple units. Okay, and then in that plane, again, have some curve, right? Okay, now what is the curve in that plane? Well, it doesn't change, right? Whether z equals 0 or z equals 2, there's no z's in here, so the z's don't affect my curve. So again, I'm getting a circle of radius 2, but this time it's been shifted up by 2 units, right? My circle's not as good this time. Okay, so I get that slice. And then I keep moving up. I keep drawing, I keep taking slices as I go up the z-axis. These, these slices are my traces. So just a little terminology. This would be this first curve we drew. That was the trace through in the plane z equals 0. This is the trace in the plane z equals 2. And then we could take, traces through z equals 4, 3.7, etc. And then the idea is we're getting this idea of, we're getting this picture of what's happening as we change our z values, right? As I move up, I just have more and more circles stacked on top of each other, and they're all the same width, okay? So let's see, my trace through z equals 0. Oops, I had a trace through z equals 0, it looked like that. Okay, I had a trace through z equals 2, it looked like this. I had trace through z equals 4, whatever, it looks like that. I just draw more and more of these. I'm drawing them poorly, but hopefully you get the idea. And then basically I just kind of connect them. I get an idea of what's going on and what is that object. Okay, and let me clean it up a bit. It's a cylinder, right? And it actually continues on up forever, right, in this direction, and continues down forever along the z-axis forever. Okay, so it's this infinitely long cylinder, and all of the cross sections, all of these slices that I can take, all these traces are circles. Okay, so by taking these traces I get a good idea of what my surface looks like. Okay, so that's what we've done here. And this is really the technique we're going to use to graph everything. Okay, now it's clear that this is a cylinder, right? And this is kind of our usual idea of a cylinder, but actually what the word cylinder is actually a bit more general in our mathematical understanding. A cylinder is actually any two-dimensional shape, or any planar curve, they call them, that's connected by a bunch of vertical line or parallel lines. Okay, so what we have here, okay, we have these curves in R2, these circles, right? So this circle here, for instance, we could call that a planar curve because it's a curve in a plane. Okay? And then we have a bunch of these, okay? And then they're connected by these lines, right? These, I could think of this surface as being just a bunch of lines that are connecting all these horizontal circles. And that's really the definition of what a cylinder is. And that two-dimensional shape, what I'm trying to point out to you, that two-dimensional shape could be, or that planar curve could be anything. It doesn't have to be a circle. It could be, for instance, it could be a parabola, which you'll see in the textbook. And I'm going to draw a different example in a second. But let's kind of recreate what the textbook did. I'll do something similar. So maybe I have the equation. Let's see, what would be? How about y minus x squared equals 0? Okay. So again, there's no z, right? So maybe usually I'm going to get a cylinder when I'm missing a variable in my my equation in R3. So if I'm missing the z, that usually means I'm going to have a cylinder that's going upward along the z-axis. So what would this look like? Let's see, if I take the trace at z equals 0, I get a shape that looks like So this is I could basically rearrange this into y equals x squared. So the traces would look like this. It'd be parabolas, right? Okay. Remember, this is y, this is x. Okay. So I have through z equals 0, I have that parabola, and then I move up a couple units and I have a very similar parabola. Boom. And then I move, if I move down, I'd have a very similar parabola, or pretty much the same parabola. And then I connect these with vertical lines. Okay, let's do a dotted line to kind of show this is behind the others. Boom. And what I end up with is this shape. It's a parabolic cylinder. Okay. So it's basically a parabola that goes up and down. Okay. And again, the textbook has a good picture of one of these. I don't know if it's the exact same, but that's basically what it looks like. Okay. So again, this is a cylinder, but my top is not a circle, right? Or my ends aren't circles, even though these aren't really the ends, right? Because my shape keeps going up forever and down forever. But these cross sections are not circles. Okay, so just because it's a cylinder doesn't mean it has to be this kind of circular cylinder we're used to. So this would be another cylinder, another example. So pause it and try it on your own, first of all, and assuming you've unpaused now, I will draw this for you guys. Okay, so x squared plus z squared equals 8. So what variable is missing? I don't have my y coordinates missing right here, and my y variable is missing in my equation, right? So that's a hint to me that, okay, this is probably going to be a cylinder, and it's probably going to be stretched out along the y-axis. Okay, so let's try and draw the traces. So now maybe instead of taking traces along my z-axis, maybe I should be taking traces along my y-axis. So maybe I should be thinking about slices like planes that are going along this y-axis. Okay, so if I take a slice like this, what kind of curve am I going to get? Okay, well, think about x squared plus z squared equals, or x squared over 2 plus z squared over 8 equals 8. What kind of equation is that? Okay, this might look familiar to you, maybe not. Remember, if I just had x squared plus z squared equals 8, that'd be a parabola, or excuse me, a circle, right? But when I have these numbers underneath, that's going to give me an ellipse. So it's not going to be a perfect circle. It's going to be an ellipse. And don't worry about learning how to graph ellipses and things like that. Really, when you're doing this stuff in the course, you just need a general picture, maybe the endpoints of the ellipse, and I'll explain what I mean as I draw it. And then that's enough to give you an idea. Okay, so let's start by taking the trace through y equals 0, right? That's this plane here. Okay, the xz plane going through y equals 0. What would my curve in that plane look like? Okay, so I'd have x squared over 2 plus z squared over 8 equals 8. Okay, well, what if z was 0? Okay. Okay, if z was 0, then I would have, let's see, my equation reduced to x squared over 2 equals 8. In other words, x squared equals 16, so x equals plus or minus 4, basically. Okay. So when z is 0, okay, I would have positive 4 and negative 4. So those are going to be my kind of the edges of my ellipse. And then on the other hand, if x is 0, so if I plug x equals 0 into this equation, it reduces to z squared over 8 equals 8. In other words, z squared equals 64. So z equals plus or minus 8. So my other edges of my ellipse would be, let's see, positive 8, negative So when y equals 0, I would have this, let's see, we should draw this a bit further down. So when y equals 0, I get this ellipse that looks like this. Okay. And then as I move down, as I take slices down my y-axis, I just get more copies of that ellipse. So I have a ellipse down here. I have an ellipse over here, all along the y-axis. And I string all those together, and what does my shape look like? Let's do it in green now. So I'd maybe have this cylinder going along the y-axis. Okay, it stretches out in both directions forever. Okay. Now, hopefully you guys can extrapolate that to working with other cylinders, okay, and hopefully recognize cylinders. The kind of bulk of this section is about quadratic surfaces, which sounds intimidating, but it's really not a complicated subject. So it's got a fancy name, but don't be intimidated by it. So let's say we have an equation in the three variables x, y, and z, and at least one of those things is squared. So an equation like x squared plus y squared plus z squared equals 1, maybe x squared plus y squared plus 3z equals 0, negative x plus y plus 2z squared equals 4, etc. So we have these equations in three variables, and we see that in all of these, at least one of these terms is squared, right? Okay, so this is what we call a second degree equation in three variables, blah, 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 blah. Okay, the graphs of these things are what we call the quadratic surfaces. Okay, and that's a fancy name, but think about what's a quadratic equation that you're used to. Something like y equals x squared, okay? So the term quadratic just means we have a square term, okay? So that's all it means. So when we have equations like this, we can graph them, and as I said, their graphs are going to be what we call the quadratic surfaces. Now, we don't need to memorize, okay, this type of equation is this type of curve, etc. What we're going to do is we're going to just learn a technique to graph them. Okay, that way you can just look at them and graph them. And okay, if you want to memorize their names, or if you want to be able to, give a name to these things, great. But really, this technique is the most important thing. If you know this technique, you'll be able to look at an equation, graph it without knowing any other properties. Okay, it's very straightforward. And we're going to use the same thing we use for cylinders, traces, only it's maybe a couple other steps. So I'm going to write out the steps as I kind of see them, and then we'll do several examples. So let's say we're given an equation, an equation in the three variables x, y, and z, and at least one of those terms is squared. We got a second order equation. So we have one of these quadratic surfaces. How do we graph it? I'm going to start by just picking a direction and then I'm going to take traces along that direction. So step one would just be, I would say, just pick a direction. Okay, so maybe you always like to start by taking slices, taking traces along the z-axis. Okay, that's usually what I do. Okay, so pick any direction you want. And then what you're going to do is you're going to pick a bunch of values along, well, before you pick a bunch, let's pick one value. Let's pick one value in that direction. So if we say we're going to move along the z-axis first. Let's pick a value on the z-axis. And then I'm going to take that value and I'm going to plug it into my original equation, okay, for z, for instance. So if I choose z equals 3, I'm going to take that 3 and plug it in for z in my original equation. Okay. Once I do that, that z is going to disappear, right? It's going to be replaced with just a constant. And then I'm going to be left with an equation and two variables. And we know how to graph those. Okay. And what I'm going to do is I'm going to graph my equation and two variables in the plane that I picked. And then we're just going to, step 3 is going to be repeat that process for more values along that same axis. So if I pick the z-axis, I'm just going to take more traces, graph more traces along the z-axis. And then that's all we did for cylinders, right? But for quadratic surfaces, we should also do it in the other two directions, okay? So quadratic surfaces are a bit more complicated. It's not enough to go in just one direction. We should probably go in all three directions. So that's what step 4 is. We're just going to go in the other two directions, do the same steps in the other two directions. And then the last step is just to connect all the dots, basically connect all the traces to get a picture of what's really going on. So that might not make sense, you know, just me spouting those rules at you, those steps at you. So let's see them in action. So let's use these steps to try and graph y equals 2x squared plus z squared. Okay. Now I'll make the disclaimer, and I did this on purpose because I kind of want to demonstrate that this process works. I haven't done this Calc 3 stuff in a while. This is the first time I've taught this class, and what I'm trying to drive home is that I haven't looked, there's a whole table of equations and graphs in 12.6, and you can, you know, memorize all the different types of equations and kind of look at this and, okay, look at the table and tell what kind of graph it's going to be and all that. I haven't looked at that table. I haven't memorized anything, all right? So I'm just going to use these steps, and I'm going to try and show you that if you know these steps, you don't need to memorize a bunch of stuff. Okay, so let's just do this from scratch. So let's pick a color. How about blue? Okay, so what was my step 1? I'm going to pick a direction to take my traces along. Okay, so I got y equals 2x squared plus z squared. Let's move along, how about the z-axis? Let's start by moving along the z-axis. Okay. So I'll start by picking a value. That would be step 2, right? I'm going to pick a value along the z-axis. So I usually start by picking z equals 0. Okay. So step 1, okay, so z, let's move along the z-axis first. Step 2, let's pick z equals 0. And then let's plug, what do? We plug this 0 in for my z's in my equation. So my equation becomes y equals 2x squared plus 0. So just y equals 2x squared. Now I'm going to graph this. What's step 3? Well, we're still in step 2. I'm going to graph this equation in this plane, right? Okay, so I graph y equals 2x squared in the plane z equals 0. Okay, so what is the graph of y equals 2x squared? Let's see. If I did 1, 2, 1, okay. That parabola, that would be a parabola, and it would look like something like this. And I would keep going. Okay. All right, now let's pick, what's step 3? All right, repeats for some more values along the axis. Okay, so I'm moving along the z-axis. So let's pick, how about z equals 1? Okay. If I pick z equals 1, okay, that's my plane. And then my equation becomes y equals 2x squared plus 1 squared, so 2x squared plus 1. Now let's graph this. Okay, well, this is the same parabola, but it's been shifted it's been shifted in the y direction by 1 unit. So now instead of having, let's see, I'm in the plane z equals 1, but instead of having a parabola that's right up against the axis, it's been shifted, and let's do this one in green so we can tell the difference. It's been shifted 1 unit away. Okay, so there's this little gap here of 1 unit. Okay. Now let's pick 2. Okay, so z equals 2. Okay, so again, this is my plane that I'm working in now. All right, now my equation becomes y equals 2x squared plus 4, right? Because I square my z. So again, we'll do this curve in yellow now. This is, oops. This is again a parabola, but it's been shifted farther away from the axis. It's like 4 units away from the axis now. Okay. So I got my cross sections, and maybe that's enough to kind of extrapolate what's going to go on. As I move up my z-axis, I'm going to have more parabolas, but they're going to start getting farther and farther away from the z-axis. So maybe my next parabola would be like here, and so on. Okay. So it kind of looks like I have these parabolas, and they're kind of going outward like that. All right, so we've done that. Now what's step 4? Okay, we need to repeat the same process for other axes, all right? So now, let's see, do I have any blank? Let's pick this. So now let's repeat the same process moving along another axis. So let's move along the axis, the y-axis. How about that? Okay, clean that up. So let's look at what's our equation? Y equals 2x squared plus z squared. Now let's take traces going along the y-axis. So let's pick y equals 0. Okay, so this is my plane, and then my equation becomes 0 equals 2x squared plus z squared. Well, what is this equation? This is an ellipse, right? So if I'm, let's see, this would be the ellipse. Actually, let's see, no. This equation doesn't exist. This doesn't have a solution, all right? The only solution here is when x and z are both 0. Okay, so this is just a single point. Okay, right? Because if this left side is 0, the only way that this equation can be true is if x is 0 and z is 0. Okay, so this is just a single point at the origin. Okay, what about if y equals -1? Okay, so this is one curve, one trace. What if y equals -1? Can we have -1 equals 2x squared plus z squared? No, this is never true, right? This is a negative number. These are both positive numbers. So that's not true. So going this way, my curve doesn't even exist going in this direction. It doesn't exist in this back half of my 3-dimensional space. Okay, so let's try the front half. Let's try over here. Okay, what about when y equals positive 2? Okay, I plug 2 into my equation and I get 2 equals 2x squared plus z squared. Okay, now this is an ellipse. Okay, so I'm at the plane y equals 2, and I get an ellipse. Okay, so what does this ellipse look like? Roughly, it's a vertical ellipse. It looks like this. Okay. I go to y equals 4. Okay, so that's y equals 2. Boom. I go to y equals 4. Okay, I get the equation 4 equals 2x squared plus z squared. Okay, this is a good one. You can find nice clean values for this. Okay, this is again an ellipse. It's getting a bit bigger, like that. And then as I move this way along the y-axis, I'm getting bigger and bigger ellipses. Okay. So I've got my cross sections for my going along my y-axis. So there's only one direction left, right? Moving along the x-axis. Okay. So if I repeat the process for the x-axis, what am I going to get? Okay, so again, I'm working with the equation y equals 2x squared plus z squared. Now I'm taking traces along the x-axis. So let's see, I take, let's try x equals 0 first of all. Okay, when I plug in 0 for x, I get the equation y equals z squared. Okay, so this is a parabola. What does it look like? It's kind of a vertical parabola, kind of a parabola tilted on its side. It's going like this, right? All right, and then I do x equals 1, and my equation becomes what? Y equals 2 plus z squared. So again, this is a parabola that's been, let's see, as we move this way, we've moved this way now, right? I get a parabola that's shifted 1 unit away from the x-axis. Yeah, or 2 units away from the x-axis. So 1, now my parabola looks like this. Okay. Okay, how about x equals 2? Let's see, my equation would become y equals, let's see, 8 plus z squared. So this is another parabola that's been shifted way this way. And then I kind of get a mirror image over on this side of parabolas. Okay. All right. So kind of funky. Now the trick is to combine everything. Okay. And maybe you can get a picture, an idea of what's going on by looking at just one of these. Okay. This one, I wouldn't recommend this one. Either, these top two are nice and clear. Okay. So try and kind of combine these in your mind. Okay. We have this shape that, okay, if we take these slices along the y-axis, these vertical slices, the cross sections are going to be ellipses. And if we take these horizontal cross sections along the z-axis, cross sections are going to be parabolas. Okay, so what does that look like? Well, it turns out that's going to be kind of like a shell type shape. Okay, I've kind of tried to draw it here. Basically, it's a shell, or you could think of it as a cone that's opening outward as it moves along the y-axis. Okay, so this is the technique we use, and this is a fairly basic shape. We can get much more complicated shapes as we move along. All right, and again, maybe we don't have to go through all these steps to get an idea of what our object looks like. Maybe if we draw, if we do cross sections along a couple axes, like maybe after these first two, I could kind of tell what kind of shape I was going to have, especially this one. Okay, really, if you drew these cross sections and then just kind of connected them as you went, if you just drew enough of them, you'd really have a good idea of what's going on. Connect these, and you start getting this shell shape pretty quickly. Very rough there, but maybe you need to take a couple cross sections and you need to verify, right? Like you can't just kind of do some cross sections and just kind of guess what the end result's going to be. You have to verify. All right, so let's do a couple more examples. Okay, let's try one more example. This is one of the kind of weird ones I think people find a little bit difficult. We'll do a hyperbolic paraboloid. Okay, so not just for this particular surface, but for pretty much everything in 12.6. If we can graph these things in R2, we'll be in decent shape. So lines, circles, ellipses, parabolas, those are fairly standard. Maybe you haven't graphed a lot of ellipses, but should come back pretty quick. Maybe something you haven't done a lot of is hyperbolas. Okay. So I'll let you guys refresh yourselves on that. I'm going to use that in this problem, but I'll let you if you want to pause the video and refresh yourselves on hyperbolas before we continue, that might not be a bad idea. Okay. So y equals x squared minus z squared. Okay, so this is going to be a hyperbolic paraboloid. That's a mouthful. Let's try and find some traces. Okay, so proceeding through our steps for graphing our our surface. Let's say I want to move along the y direction first. Okay, so let's say I start with the trace y equals 0. Okay, so I'm in the plane y equals 0. Okay, my equation becomes 0 equals x squared minus z squared, which is the same as x squared equals z squared. Well, this is true if and only if square root of x equals square root of z. Okay, so this is basic. We're going to be working with the hyperbolas when we're moving along the y-axis for this equation. So for hyperbolas, we usually have this kind of center case when we have x squared equals z squared. Okay, that's going to give us just intersecting lines, basically. I'll do it in blue. The way you can think about this, okay, if you're at x equals 2, for instance, okay, x equals 2, okay, so here you're going to have square root of 2 is 2. Okay, so that means absolute value of 2 is 2. So when you're at x equals 2, you know that absolute value of z has to be 2 as well. Okay, so z could be positive 2 or negative 2. So z could be up here or down here. Okay, and if you go to x equals 3, well, z could be there or there. And so you get these lines that kind of look like absolute value graphs, or, you know, an X basically. Okay. So that's in the XZ plane. Okay. Now let's move to y equals 1. Okay. When I have y equals 1, I have this standard hyperbola equation. So 1 equals x squared minus z squared. Okay, that's going to be a hyperbola. It's going to have, we're going to be in this plane, y1. Okay, the vertex is going to be at x1, z0, and -1, z0. So like this. Okay, and then as we move out, we're going to, if we did y equals 2, how I would suggest you deal with this is, okay, you get this equation, 2 equals x squared minus z squared. The way I deal with this for the hyperbolas is I divide out the 2. Okay, and that tells me my parabola has vertex, let's see, positive 2, positive x, let's see, x equals positive 2, z equals 0. So there are these hyperbolas that are kind of moving away from the y-axis. Okay. So these these hyperbolas are kind of moving farther away. Okay. So that's those traces. Okay. Now what happens when we move, when y is -1? Something, when we kind of move into the negative y's, something interesting happens. Okay. So let's say I had, I tried to trace y equals -1. Okay. So my equation becomes -1 equals x squared minus z squared. Divide out -1, the negative sign, and you get 1 equals z squared minus x squared. Okay. So this is still a hyperbola, but now it's going to be going the other direction, right? Now the parabola is going to be going, as I move this way along the y-axis, my hyperbola, excuse me, I probably keep calling it parabola. My hyperbola should be kind of vertically oriented, going this way. So I'll do these in green. Then as I move out this way, they should be getting farther away vertically. Okay. So hopefully you can see what's going on with those. Okay. Now let's do traces in the, let's see, we just did y's. Let's do traces along the x-axis. Okay. So again, I have the equation y equals x squared minus z squared. Okay. How about x equals 0? Well, then I get the equation y equals -z squared. That is, let's see, it'd be the parabola going yz. It would look like this in the yz plane, right? It's a flipped parabola. Okay. And then if I did, okay, x equals 1, I ended up with y equals 1 minus z squared. So y equals -z squared plus 1. That would be the parabola, the flipped parabola that's been shifted up by 1. So something like when I move this way, when I'm at x equals 1, something like this. Same thing when x equals -1. Okay. Then when x equals 2, it's shifted up by 4. Okay, so I have these parabolas. And then so we've done along the y-axis, along the x-axis, now the z-axis. Okay, so how about z equals 0? Well, I just get y equals x squared, which is what? This parabola. When z equals 1, okay, so I get y equals x squared in that case. When z equals 1, I get y equals x squared minus 1. So parabola that's been shifted down by 1. So I move up 1 unit in the z direction, and then I move back 1 unit in the y direction. Okay. Then if I go to z2, it's shifted back 4 units, right? Okay. And then the opposite going this way, down the z-axis. Okay, so I get these 3 sets of traces, and it might be kind of confusing. And here's where looking at the table of curves can help. You know, if you can do this, you know, if you're sharp, you can do this just by kind of putting them together in your mind. But if I was going to be doing a lot of graphing like this, I would keep some table handy. You know, it's fine. It's all well and good to be able to, you know, just look at the equations and try and draw them. But having that table helps just, you know, make things go a bit quicker. So looking at my table, I kind of get an idea of what my graph's going to look like. It's basically going to be a saddle, right? Where you're going to have hyperbolas in one direction, and then everything else is going to be parabolas. So let's see if I can draw this. Okay. So I know going this way, I have these kind of vertical hyperbolas. So hyperbolas like this, right? Okay. And then going along the y direction, I know I have hyperbolas, horizontal hyperbolas. Okay. So basically what I have is, and then everything else is parabolas. So let's see if I can draw this. So going that way, it looks like this. Come to one of these saddle points, they're called. So this is a really rough sketch of what's going on. If you go to your book, this was exercise number 28. If you go into your book and look at graph number 5, that is the correct answer for this. problem, you get a clearer picture of what's going on. I apologize for my horrible 3D drawing skills. These are hard to draw, so if you're having trouble similarly, don't feel too bad. I'm going to stop there. I don't know how many examples I said I'd do. I'm going to stop there. And another difficult one is hyperboloid of 2 sheets and maybe even hyperboloid of 1 sheet. It's kind of weird. So we can cover those in the lecture on the 15th.